In the previous sections, we talked a lot about functions. However, we always use them with positional parameters, and these parameters are mapped by their position, meaning that the first argument is mapped to the first parameter and the second one to the second parameter, and so on. However, there's another type of parameters in Reason which are called labeled parameters. And these parameters are not determined by their position, but by the name of their label. So it doesn't matter in which order are these arguments applied, as long as they are correctly labeled. But first, let's take a look at an example with positional parameters. We defined the divide function, which expects two positional arguments and returns their division. However, since both arguments are of the same type, it's easy to make a mistake when calling this function by accidentally applying arguments in the wrong order. In our example, it's a significant problem because if we apply arguments in the wrong order, we will get a different result. Or the function might even crash, as you can see in this example. So the question is it possible to avoid such mistakes? It is. Let's rewrite our function with labeled arguments. As you can see, we can attach labels to parameters by prefixing them with this tilde symbol here and here. And by doing that, we are declaring that our function accepts two labeled arguments, integer 1 and integer 2. When calling the function, we also need to make clear which argument we are currently passing by explicitly using its label, as you can see here. In our example, we first passed integer 1 with the value of 0, and then integer 2 with the value of 10. Moreover, functions with labeled parameters are more versatile than functions with positional ones, because we can provide arguments in any order. This time, we first passed integer 2 argument and then integer 1 argument, and our function still works the same. In the previous section, we learned that all functions in Reason can be partially applied. So we can partially apply our function with labeled parameters as well. When we call our function with only the first labeled argument, we get back a function expecting the second one, as you can see here. On the other hand, when we call our function with only the second labeled argument, we get back a function expecting the first one. As you can see, the usage of labeled arguments significantly decreases a possibility that we pass our arguments in the wrong order, because arguments labels are bound to parameters labels. In our example, we used the same name for the label and for the parameter. We took an advantage of so-called punning, which enables us to use syntax shorthand when the name of the parameter and of its label are the same. And we did this here. We write the name only once. Without this shorthand, our function looks like this. As you can see, this version is more verbose because we have the name duplicity here. However, we can take advantage of using a distinct label and a name for a parameter, because labels of our parameters are pretty long, as you can see. In most cases, we are writing long names to make our code more readable. However, using these long names in the function's body can make our code unnecessarily verbose. So let's rewrite our example with separate names for labels and for parameters. Now, labels of both parameters are still the same, integer1 and integer2. However, we changed the names of parameters. They are called a and b. As a result, the body of our function is more concise, since we are referring to the parameters using single letters. Let's take a look at our divide function again. And let's say that there's a possibility that one of its expected arguments might be missing. To address this scenario, we need to be able to use optional parameters in our function. And in Reason, we can do that. Let's take a look. As you can see, we run our code and we got a warning from the compiler. But let's ignore it for now. We defined the multiply function whose second parameter, integer2, is optional. And if the optional argument is missing, our function will return integer1. Otherwise, it will multiply integer1 by integer2 and return the result. The optional parameter is written using an equal sign with the question mark. When using this optional parameter syntax, integer2 is automatically wrapped in the option variant type. And we've already talked about this predefined variant in detail in one of the previous sections. Here's a quick recap of how the option type looks like. The value of the option type is either none, meaning it's not existent, or it's a value that is wrapped using sum. This means whenever we are pattern matching the option type, we always need to cover these two cases. And it's what we did in our example. In our example, if we call our function and omit the optional argument integer2, this argument would get a value of none. On the other hand, if the argument is provided, it will be wrapped using sum. So the value of integer2 can be either none or sum holding the value of an integer. Let's try to call our function, and let's also remove the option type because we won't need it. As you can see, we called the multiply function without the optional argument integer2. However, instead of the result, we got back a new function expecting the optional argument integer2. What happened is that we partially applied our function. But why is this not working? Well, let's read the compiler's warning from the earlier. It's telling us that we cannot call this function without the optional parameter. It seems that the compiler thinks we are partially applying our function and that we will pass the remaining argument later. As a result, the compiler is waiting until all the arguments are passed. It's basically ignoring the fact that our second parameter is optional. Let's try to fix it. We added pairs of parentheses to the function definition and to the function call. These parentheses are in fact the unit type, and now our function works without the optional parameter. So what happened? If we take a look at the function type, it's expecting 3 parameters now, and the last one is unit. Without the unit type, the compiler didn't know if we wanted to pass the remaining argument later or we didn't want to pass it at all because it's optional. Moreover, the order in which we are passing arguments is not helpful to the compiler, since the labeled arguments can be passed in any order. To tell the compiler that we just want to call the function and don't want to pass any other arguments, we need to always use at least one positional parameter. And we are using the unit type as a convention. When we use the positional parameter, in our case the unit type, inside the function definition, the compiler presumes that the optional argument is omitted when the positional argument is provided during the function call. So when we call our function with the unit type here, as the positional argument, the compiler knows that we finished calling this function. It presumes that the optional argument is omitted and the function will be executed. In reality, we can pass any positional argument. However, passing the unit type is a convention. When the compiler encounters the first positional argument in the function call, all the optional parameters that are missing will automatically get a value of none, and our function gets evaluated. This means that we need to pass a positional argument to trigger function execution. Let's call our function without the positional argument. As you can see, we passed only a single argument. And because we didn't pass the unit type, the compiler concluded that this is the partial application. So we are getting back a new function expecting our optional argument and the unit type. Let's take a look at another example. And let's also remove these two function calls. We created the payload identifier holding the optional value sum, holding an integer. And we also created the result identifier. Here we pattern match payload, and then we call the multiply function depending on the payload's value. In other words, if the payload is sum, we want to pass it as an optional argument to our multiply function. Otherwise, we want to omit this optional argument. The most straightforward approach to achieve this is to use pattern matching to check whether payload's value is none or some, like we did here. However, there's a more concise way to achieve this. As you can see, this code is much shorter. We are not doing any pattern matching anymore. Instead, we are telling the compiler that the payload has a type of an option. And the compiler will pass this whole payload option wrapper as the second argument to our function. As a result, the multiply function will be called with the integer2 optional argument or without it, depending on the value of the payload option type. If it's sum, the argument will be passed, otherwise our function will be called without it. So we know how to handle optional parameters. However, sometimes having a value or don't have it at all is not enough. For these cases, Reason provides us with another way to deal with possibly missing arguments. We can write optional parameters with the default value and decide what will be the value of our argument if it's not explicitly passed. Let's take a look. Now, our multiply function has both parameters defined as default ones. Integer1 has a default value of 5, and integer2 has a default value of 7. So, when we omit one of the parameters during the function call, the compiler fills in default values for missing optional parameters. When we omitted the first two arguments and called our function only with the unit type here, both default parameters were used, and we got back our result. That's right, although this looks like we are calling a function without any arguments. In fact, we are passing the unit type. And we are passing the unit type to tell the compiler that we are done with passing arguments, and the compiler can therefore execute our function. When we called our function without the integer2 optional argument here, only this argument's default value was used, and we got back our result.